In the meanwhile, I'll also have connected over the tab in case I need to write something.
Yes, sir. We are live, sir. Please, we can start.
Sure. In the meanwhile, I'll also have connected over the tab in case I need to write something.
You can mute the YouTube video. You can mute, sir. We can start.
Sure. Yeah. So there is no echo right now, right?
Yes, sir.
Okay, so I'll just turn on the video in a bit. First, let me welcome the participants. So you said there are 6 people waiting, Balaji?
Yes, sir.
Okay.
Yeah.
So welcome to the live session for the Applied Time Series Analysis course that's currently running. And this is a 12-week course, just to remind you. And hopefully you've been having a very productive journey and you've been learning quite a bit about the concepts of random variables, random processes, and so on. Of course, we have quite a bit of journey left. This live session is to essentially enable you to ask questions pertaining to the videos that you have seen. And it could be those that have been answered, but you were not satisfied or things were not clear to you, or it could be a new set of questions. So the floor is open to questions. It's all yours. So is there any question in the chat window? Okay, is there any Zoom meeting is what Parimala is asking. No, there is no Zoom meeting link for the participants. Yeah, good morning. All the questions have to be typed in the chat window on YouTube. That's the way, right, Balaji? I think that is how it is.
Sir?
Yes, Raghav.
Sir, since only 6 or 5 people are there, maybe we can share the Zoom link.
No,
we can interact face to face.
Yeah, we can do that, but I don't know if that's going to be the case for the next 1 hour. I'm not so sure how many have agreed to participate.
Sure, sir.
If we are sure that there are only about 6 or 7 people, yeah, then certainly we can have a Zoom link. But I think the idea is to have this YouTube live recorded. So this recording of this will be posted.
Right, sir. Sure.
With a Zoom, then it becomes a bit cumbersome to record.
No, sir. But this is already streaming live. So if they come on Zoom, even they will be stream live. That's it.
Yeah, it's okay.
Sure.
So let's actually ask them to type the questions. Parimala, Raman, and Subramanian, if you have any questions, yeah, please feel free. This is your opportunity. So we have about, I think, 1,200 participants, don't we? People who have enrolled.
Yes, sir.
Okay, so there is some question here. Let's take the questions in the order they appear. The question is on randomness. In the lectures, from an engineering standpoint, the random process, physical process plus measurement process, source of randomness is generally in the measuring instrument. In the case of a business problem, okay, good question. Okay, so let's address the question of randomness first. Before I do that, Balaji, are you around? I just wanted him to let me in. Yeah, just give me a minute here.
Sir, we cannot hear you.
Yeah. I'm sorry. Yeah. Now I'm so sorry. Yeah, I forgot about it. So yes. So I hope you are able to hear now.
Yes, sir.
So let me just start explaining again. So here I've drawn the sketch of a process, and this process could be anything. It could be an engineering process or a business process, doesn't matter, which is generating this variable of interest. And the star there denotes the true response that you get. And then you have, let's say, the measured response, which is differing from the truth by this, let's say, some VK. Okay. So the difference between Y and Y star is VK. That we know. And what is the source of VK? For now, let us assume that the source of VK, which is the uncertainty in YK, that source is a sensor. But in general, you can have contributions to VK even from the some unmeasured we call them as disturbances, but it could be unmeasured factors. We don't know what those factors are, but they are also contributing to what you are observing. And this could be either at the sensing side or at the excitation side. I'll talk about it. So let me draw even more general schematic here. So here you have, in fact, I have drawn this schematic even in the lecture. So let's call the signal or the input that is exciting the process, or the factors that are exciting the process, by UK. So this is a setup that we have. And the randomness that occurs in Y, as per what I have drawn here, is occurring at the output side. And this VK is the one that we can assume to be random to begin with. And what is the source of randomness in VK? The sensing element. Now, on the other hand, Y star itself can contain randomness of its own. Now, you may wonder how can the response, the true response of a process be random? Well, that's because inherently there are many processes that behave in a stochastic way. That means even if you had an ideal sensor, even if you had no external factors affecting Y star and only UK was generating Y star, then you will still see randomness in Y star. Why does randomness occur in Y star? Well, again, you must recall that randomness is a term that we give to our ignorance. That means we do not truly understand the relationship between the input U and the response Y star. Whenever that happens, you can say that the process is also random. In fact, broadly speaking, you will find two classes of noise, namely process noise and the other one being measurement noise. There is also another noise that occurs, that occurs at the output, which we say is due to the effects of unmeasured disturbances. And these disturbances can be at the output end or at the input end. So these are the three broad sources of uncertainty that you will find in any variable. But do all of them have to be active is the question. Okay. In any given process, are all the three sources of randomness active is the question. So let me complete the schematic here and then we'll answer that question very soon. So when I say process noise here, the process noise is internal to the process. So this is where you can say inherently stochastic. So this process could be inherently stochastic. That means I cannot predict its behavior, even if you were to give me the true response and the true excitation signal that you have. Every time I perform the experiment, it produces a slightly different response, and I'm unable to explain why that is happening. And when we think of that, we think of an ideal sensor. We think of, likewise here, we could think of this UK as being a sum of, now we can say that this UK is actually a sum of two things. Now I'm coming to the effects of unmeasured disturbances. So let's say that you have actually designed U star, but there is some disturbance at the input side, which is superimposing on the input that you gave, and the process is actually excited, not just due to U star, but U star plus DU. right? This Vk here is made up of two things. Again, you have dy and sensor noise w. So this is the sensor noise. And here we say that we have the output disturbance. So look at how many different sources of randomness can exist. That means the randomness in your observations can enter through different channels. One is through the input disturbance, other is through the sensor, and other is through the output disturbance. Apart from these three, the process itself can be inherently random. That's because the process is unfortunately it cannot be mathematically modeled accurately. Now, when it comes to a business process, let's say when I say, I presume that when Raman said in the case of a business problem, he means that he's referring to some econometrics process and so on. In those processes, generally the measurement noise is absent because let us take the example of a stock price. When I'm looking at a stock price, there is no question of a measurement noise there because it's a calculated quantity. And unless I make a mistake in the entry in my database, there is no question of a measurement error. On the other hand, there could be process noise. So that can be a major source of randomness, and that is in fact the major source of noise in many, in fact, all econometric processes, in all financial processes that you see, the process noise is a predominant one. Measurement noise is absent. Let me also give you another example from sports domain. So suppose I am predicting, let us say, the score of a cricket match. Obviously, I cannot predict accurately. There is no measurement noise in the data that I have. So I have historical data of a particular team A, which is going to play the next match against team B. I have the historical data. There is no measurement error in that. Then what could be the source of stochasticity? I cannot predict it accurately. So I have labeled it as random. The major source of stochasticity there is the process noise. Okay, you can say there may be some output disturbance because it depends on now whether you are going to model the input-output relationship or only you are forecasting Y with its own past. So typically there are these two classes of problems, right? You're only given the series Y as against you're given the series Y and also U star. So let us say you want to model the relationship between the balls, the speed of bowling by a particular bowler and the run scored by that particular player. So the speed of the ball and maybe the angle of the ball, these are all the inputs. The angle of the ball bowled by the bowler. And YK is the runs scored. In that case, there is no measurement noise, but there can be output disturbance because there can be wind blowing in the stadium. And that can affect whatever you're observing. Apart from that, you have process noise. And there could be input disturbance also. That is, as the ball is being bowled, there is wind affecting it. And as the batsman hits it, there could also be the effect of wind in swaying the ball. So there could be both output disturbance and input disturbance, but there is certainly process noise. There is no measurement noise. So hopefully now you have an understanding, a much better understanding of what is the difference of in terms of randomness across different processes. And it's a good exercise to take a few examples from different domains and segregate or identify the sources of randomness so that you are very clear in your mind what are these three broad different sources of randomness in your data, and that which you have to respect. So hopefully it answers Raman's question. Let's take the next question. So Mr. Subramanian is asking if he can provide solution for the numericals in quiz. I think the TAs, Ranga, Raghav, Nitya, I think we should be able to do that, right?
Yes, sir.
I think we need to do it soon, perhaps.
Yes,
That's
sir.
all.
We'll do that.
Okay. Now, the next question is: is low autocorrelation indicative of stationarity? What do you think? Let the TAs answer this question, and then of course I'll add to that. Ranga, you want to take that question? Nitya or Raghav? Does low autocorrelation mean stationarity? Is there a connection between these two?
No, sir.
Yeah,
Raghav,
okay.
no.
Obviously, no, right? So
No,
there is no
because
connection
vitals.
between the magnitude of autocorrelation and stationarity. Stationarity simply says that the autocorrelation should be a function of the lag, but doesn't impose anything on the magnitude of autocorrelation. Of course, by their own definition, autocorrelations have to be less than 1 in magnitude. That has got nothing to do with stationarity.
Right.
So low autocorrelation essentially means weak linear dependence across observations at that lag. That's all. Is there anything else that we have to mention with regards to that question?
No, sir, I think we answered.
Yeah, so I think it's a straightforward answer, but I'm curious as to why that thought came about. Why there is a thought that low magnitude of autocorrelation can be related to stationarity. If there is any misconception there, I would like to address that. Okay, so I think there's a small lag. As we speak of lags, there's a small lag between what I speak and what appears on YouTube. Therefore, we'll have to give a few seconds for them to respond. So in the meanwhile, I just wanted to ask the TAs, do you think there was some unanswered question in the forum that we wanted to answer live? Is there anything like that?
Sir, there were like repeated questions about this course and system identification. We have answered that question, but if you can explain that, I think that would be helpful.
Yeah, in fact, that's a good point. So this diagram is actually helpful. The schematic is helpful in answering that. The difference between time series analysis and system identification is pretty clear. In time series analysis, at least let's take the univariate time series analysis. The univariate time series analysis deals with the forecasting or modeling of YK given its own history. No knowledge of the exciting signal U is available. In time series language, we call UK or U star as exogenous signals. On the other hand, in system identification, we are given UK as well. So time series analysis, time series analysis, you have only YK available, and sys ID, you have YK as well as the knowledge of UK or U star, one of those. And the primary goal in SysID, system identification, is to develop a model between the causal signal U and the effect Y. Whereas and of course, for the purposes of predicting Y, the final end use of the model is the same as in PSA. Because in time series analysis, the cause information is not available, at least in the univariate case, we try to come up with a fictitious cause. That's where we end up with white noise. But the most important thing to remember is we start off by saying yk is random, and then we assume that it is stationary and so on. Whereas in system identification, we don't start with assumptions that yk is random and so on. We recognize that yk is made up of two components, y star and vk. And we believe that y star is because, let us ignore the input disturbances for a moment. So we believe that y star is solely driven by u star, and vk is a stochasticity that I have to account for in my measurement. So the object of interest in system identification is the process that relates u or u star to y. And in doing that, one has to recognize that there is a stochastic component y, which we cannot ignore. And if we make wrong assumptions about vk, the model between u star and y star can go wrong. So in terms of the information and in terms of the centerpiece, time series analysis and seasonality are quite different. But they are very similar in the sense that both actually take into account the stochasticity, and in seasonality we assume vk is stationary, and then we use time series analysis concepts to model vk. And as I said in the forum, historically system identification has evolved from time series analysis, where the effects of u star or uk are modeled as effects of exogenous variables. Okay, so that's the difference, and hopefully that was clear. So we have Devnath asking, find your course while looking for wavelets, and okay, very good. Please advise in which order should I approach the courses of time series analysis and okay. And that's a good question. Well, not sure if there is a unique answer to that unique sequence, but I'll give my recommendation. As I just said, system identification is dealing with a mixed problem. What we mean by mixed problem is it's looking at y star and vk coming together, and it's trying to explain. So it's this idea. You are trying to explain yk as a sum of two effects. And we believe that y star is driven by u star, let us say. And vk is, we don't know what causes changes in vk. So we're dealing with a composite signal in y. And typically we assume that y star, the process that produces y star as a result of the input u star, is deterministic. So it's a good practice, therefore, to get a grip on deterministic processes, deterministic linear time invariant systems, and signal processing of deterministic signals and so on. In that sense, the time frequency analysis and wavelet transforms will help you to a large extent, not completely, because the time frequency analysis course does not teach you much on the linear systems theory part, because that is a very essential concept or topic when it comes to system identification. Naturally, you need to have some good base on time series analysis if you want to have a smooth sail in society. Therefore, it is always preferred that you do time series analysis prior to studying system identification. It will help a lot. So the recommendation that I have is you start with time frequency analysis and wavelet transforms, because it deals with a nice world of deterministic signals. It will teach you sampling concepts, sampling theorem, signal processing, Fourier transforms, a lot of things that you need to know about processing deterministic signals. And then you move on to time series analysis, where you learn a lot about modeling random signals. I think then you are in a very good position to take on SysID. But that doesn't mean that if you have not done these two, you will find a SysID impossible. Yes, the learning curve can be steeper, but if you go to the lectures that I have on system identification or the book that I have, it's a one-stop resource. So you should be able to learn all at one place, and you will find the same sequence there as well. The only difference is I start off with deterministic LTI systems first, and then move on to random processes, as against starting with time frequency analysis. That's slightly advanced for SysID. There is some overlap between the theory of deterministic systems that is required for SysID and time frequency analysis. But that's a sequence in which I teach. So you should be comfortable there as well. But generally speaking, yes, SysID is better understood after you do your courses on time frequency analysis and the TSA. So hopefully that answers Arun Utpal's question. Okay, so Raman has a question on seasonality. In the meanwhile, I see that Nitya has answered a question. Oh, sorry, you have pasted a question, Nitya. Is that the case? That we have not
Yes,
answered?
Yes, yes.
Okay. Okay, so let's answer this question and then come to seasonality. The question is asking or is pertaining to choosing AR2 over ARIMA for the example that I took up in the lecture. And the reason I gave was unique estimates, even though the actual DGP was ARIMA, but unknown to the estimator. So what is the meaning if uniqueness preference of AR models? Does it mean that ARIMA estimated model question will not be unique? Oh yeah. You need not get the same coefficients with for the ARIMA model, even if the data set is the same, because it depends on the initial guess that you have to provide for the estimates. See, you know that the predictors associated with ARIMA models are non-linear in parameters. So when you are either solving the maximum likelihood estimation or the nonlinear least squares or the least squares approach, you will end up with a nonlinear optimization problem. And we all know that nonlinear optimization problems require initial guesses. So if you change the initial guess for the same data set, you can have a different final answer. Secondly, the tolerance criteria that we use to terminate the optimization can or do, in fact, not can, they also influence the final parameter estimates that you have. So if you keep the initial guess the same, the tolerance criterion and the search algorithm parameter. So there is, again, there are some hyperparameters in the search algorithm. If the hyperparameters are also kept fixed, then you'll get the same answer. But that's unlikely in the sense uniqueness should not depend on these things. Uniqueness is for a given data set, you should get the same answer regardless of what the user does. That unfortunately is not guaranteed with ARIMA models. Whereas with AR2 models, you are guaranteed unique estimates because, as you will see later on, the predictors are linear in parameters. And typically, you will use a least squares method or a Euler-Walker method. If you use the least squares method, you will be solving a linear least squares problem, in which case you will have a unique answer. So whenever you give the same data set, you will get the same answer because there is no other user intervention that is required. And likewise for Euler-Walker. With ARIMA, as I mentioned earlier, user intervention is required in terms of initial guesses, specifying the terminating or the tolerance criterion, and then the parameters of the search algorithm. All these require they can vary from user to user. Therefore, the uniqueness is not guaranteed. That's the point. Okay, so hopefully it answers the question that was raised. Yeah, thanks, Jalesh, for endorsing my recommendation. Yeah, it's always preferable to do time series analysis before you do SysID. But having said that, there are a few students always in my SysID course here, in the semester course that I teach, who take up SysID before doing TSA. And they do well, but today they have the advantage of sitting through the time series analysis lectures. At least they can have a quick preview before they sit in SysID. And in the course that I teach on SysID, now this can vary from instructor to instructor. When I teach SysID, I certainly make sure that I review the time series analysis concepts, but that cannot be guaranteed of every person who teaches SysID. They may assume that you have the time series analysis background. So you have to check with the instructor before you take up SysID. Okay, so let's go to the question that on seasonality. How to handle for seasonality in time series when festivals like Diwali occur in different months each year? Okay. A good question, because unlike Christmas, our festivals are lunar calendar based, and obviously it's not going to be the same. Now, agreed that you, if you were to follow the sales date wise, you will not see a perfect periodicity, and therefore you will have to actually turn to a bit of Sarima modeling, or you can say that in fact, you can actually calculate when these things will occur, and you can adjust, because the Diwali that's going to occur for the next 100 years, you can calculate accurately. All the calculations, the almanac calculations are there. It's not that you cannot say it is random, I don't know when Diwali will occur this year, and so on. So you can account for it. One way is to pretend that when I cannot calculate it accurately and model it as a Sarima model, or I'm just thinking what could be the other way. The other way is to index it in a different way. So you don't index it in time, and maybe you use a different index of time. You don't use the index of observations, because in the index of observations, it's not exactly periodic. But if you use a different time index, then it's likely to be periodic, but then the stochasticity can take a beating. So what happens is, that is what they call as cyclicity in time series language, time series analysis language, because you don't see this exactly occurring at the same time. And also remember, the cloth sales are not going to peak by the same value every year. Your periodicity now will be in a certain range in your data, but it's going to be a very narrow range. And therefore, you may need sinusoids of slightly different frequencies, but you don't need many frequencies. You will need a finite number of frequencies, and then you can model the periodicity. So that might be a solution. You cannot remove or account for the periodicity or the seasonality by a single sine wave. You will need multiple sine waves of very closely spaced frequencies or periodicities, and you should be able to explain that. Okay, because pretty sure, right? I mean, if you follow the almanac, you will see Diwali coming back more or less to the same date after certain number of years. So you should be able to see that Diwali occurs on the same day after a certain number of maybe some decades. Depends on the moon's movement. Yeah, so this is one way. This is another way of modeling the seasonality for that accounts for festivities. There may be other solutions. I'm not saying that I have thought about this, but I'll think about it. It's a good question. If there are other approaches, I will certainly post them on the forum. You can remind me if I don't. So the question is, analyze the time series data given week for and suggest suitable model. This was a question quiz for which model determining the suitability. I don't understand. What does it mean? Do you follow Ranga, Nitya, Raghav? This question that talks about model determining the suitability. What was the question about?
Sir, I believe it's a data given and they have to determine the best suitable model among the options.
Okay, there's no fitting that they have to do. They just have to identify or pick the most suitable model. They don't have to.
They will have
They have
to fit and check the resulting values or AIC criteria.
Oh, I see. So you have gone. Okay. So what do you make of this question here? I'm unable to answer. Which model determines? There are 4 models given in the question. Okay. So let me assume that basically the question is asking what helps you determine the suitability of the model. Would that be a correct interpretation? What do you think, Raghav?
Yes, sir. I think what determines the suitability. So we can say AIC criteria or something.
Yeah. So there are different criteria. Now, model selection is an open-ended problem even today. It is as old as it is new today. And over the decades, many criteria have evolved in helping the users select a particular model. The guidelines, though, have remained the same. Okay. The guideline is that you want to make sure that your model is neither an underfit nor an overfit, and your model is as simple as possible. So these are the 3. And then finally, of course, you can talk of the reliability of the model, uncertainty. All of that is taken care in underfit and overfit. So by and large, the criteria that are used popularly for determining the suitability of a model is the trade-off between bias and what do you say? Bias and variance. Let me actually. So you have what we call as bias, and then you have variance. So the trade-off between these two is the one that allows us to come up with a suitable model. So if I choose too simple a model, okay, then let me actually plot it here. It's better that I plot. And let's say I have here bias, and here I have variance. So if I choose a model that is very simple, it will have a high bias but a low variance. So this point here corresponds to wanted them to what Nitya is. Yeah, I thought so. In fact, it's not about estimating at all, because week 4 is a bit early for them to estimate. In any case, I've started the discussion. Let me explain this. But as far as the timing of the question is concerned, that which was in week 4, all we are expecting is you to use the ACF and PACF plots to decide on the model. That's all, right, Raghav? I think that's all it is, Nitya. Anyway, let me complete this. So this is actually corresponding to a simple model. What we mean by simple model is fewer parameters, typically the low complexity model. And on the other hand, there is another point here which corresponds to this point here, corresponds to highly complex model. And of course, not a straight line connection. Yeah, exactly. But anyway, since we have taken this opportunity, we'll do it this way. So you have here, as you move from highly complex models to simple models, you will gain on the variance. Obviously, what we mean by variance is here, variance of parameter estimates. Or you can say the variability in your predictions eventually. And here we say bias in the fit. So as you move from the highly complex model to simple model, you will gain on the variance, but you lose out on the bias. So somewhere we'll have to find a trade-off, and AIC, BIC try to find this trade-off somewhere here, and so on. They're trying to get you the trade-off point by quantifying what is the effect of number of parameters on the bias relative to, of course, the number of data points, and what is the effect of the number of parameters in your model on the variance. So you have AIC, you have BIC, you also have minimum description length, final prediction error criterion, so many different criterion. These are the things that you will have to worry about when you go to estimation. But as far as the question in week 4 is concerned, you don't have to think about these. You'll just have to think about the autocorrelation function and PACF. And the guideline there is, if you find that the PACF goes almost abruptly to 0, that is, becomes insignificant after a few lags, and the ACF is decaying slowly, relatively, it doesn't decay, it doesn't go down abruptly, then you would pick an AR model. And vice versa for an MA model, if both decay slowly or kind of exponentially, they don't decay abruptly and the orders are maybe high, then that is the lags at which, up to which they decay exponentially are high, then you want to pick an ARMA model. That is the basic guideline. That's enough for that particular question. Okay, so now Jalesh had a question. Is it possible to use delay with regards to the seasonality question? Which seasonality question is Jalesh referring to? Any idea? Ranga or Nitya Bhagav, do we know which seasonality question he might be referring to? Oh, you mean the seasonality question that Raman had asked?
No, Diwali question.
Diwali question. Okay. Delay, I don't know what is meant by delay in time series models, because we don't look at any inputs. So it's all about including that particular lag. But that is exactly what seasonality is doing. See, do not view seasonality or seasonal models as something separate. The reason for giving special attention to seasonality is as follows. So when we think of seasonality, why is seasonality considered separately or given due attention in time series models? Because let us say that I have a series VK, which is, let's say, following an AR1 process, and you have this. But because of seasonal effects, there may be another contribution which occurs. So there are two processes running in parallel. One is the process, one is a correlation at the regular time scale, and the other is a correlation that is occurring at the seasonal scale. Now, if you don't subscribe to that thought, then this is also an AR model only. It is, after all, an autoregressive model of order S, because S is going to be greater than 1. But it has a special structure. The structure that is special here is that the intermediate coefficients are 0. So there is a difference between an ARS model and a seasonal, let's say, SAR1 model. Okay, let's say one in regular scale and one in at the seasonal scale. So let's say here SAR1, but we generally write 1 here and say it is at the scale of 12. Okay. So there's a difference between these two. When I say 12 here, let me write S so that you're not confused. And you know the difference straight away. All the intermediate coefficients are 0 in the seasonal AR model. And that's all, and that is what makes a big difference, because if you have to estimate all those intermediate coefficients, then you would be unnecessarily wasting your effort and increasing the variance of the parameter estimates for D1 and D1S. Whereas you can afford to have reliable estimates of D1 and D1S by putting in the knowledge that you have a seasonality. That is the prime reason why seasonality or seasonal models are given separate attention. Now, when you have Diwali-like events where the seasonality is not fixed exactly, then you will need a few more terms there. It may be not S, it may be S1, S2, S3, but still it becomes, you can say that it is now not exactly a seasonal model. You can say that it is an AR model of some seasonality with a lot of coefficients going to 0. So you can solve a constrained AR parameter estimation problem. But there is no notion of delay here. There is no notion of delay. In fact, as I discussed, I don't know if I've yet come to that, but later on when we talk of seasonality, I will also perhaps post some additional lecture notes that I gave in the later years, because this was recorded in 2016. There is a difference between this model and the other model, where you have Vk equals exactly a periodic component plus a stochastic component at the regular scale. Plus you have minus D1, let's say Vk minus 1 plus Ek. So this periodic component can be replaced with a sinusoid or a cosine. It becomes a deterministic function. So there is a subtle difference between the one that I have written on the top and the one that I have written at the bottom. You will have to choose according to the phenomenon. We'll come back to this question when we talk of seasonal ARIMA models briefly in the course later on. Okay. So there are 4 models given in the question. What should I calculate? Well, for that question, you will have to look at the ACF and PACF and then follow the guidelines that I just gave. Okay, then the next question is on autocorrelation. If we plot the ACF of a time series and find the ACF first 3 lags is statistically significant. And okay, then should we neglect this? Okay, this is always a standard question. Now, in order to address these questions, you need to turn to a better hypothesis test. So one way, of course, is to give them the due respect and model and choose a model that captures the autocorrelation at lags 8 and 9. The other way is to build an build a model that captures the significant autocorrelations up to lag 3 and see if the residuals have anything to offer. Otherwise, there is no other way to solve this problem straight away. You cannot straight away look at that and say, hey, I should worry about lags 8 and 9 and so on. But yeah, there will be always this stray correlation, I mean the autocorrelation coefficient slightly outside the significance band. But remember, the significance band itself is an approximate one. And therefore, if you find minor excursions out of those 95%, 99% bands, generally you don't have to worry so much about it. Because in order to capture the last, I mean, those small ones, you will end up unnecessarily complicating the model, and you will compromise a lot on the variance of parameter estimates or errors in parameter estimates. As a result, the model will perform poorly on test data. So it's like, you're cleaning the house, you've cleaned 95% of the house, 98%. And now you start spending time on clearing the last 1%, which is going to be there anyways. So you just leave it and keep moving. But as I said, you can follow that procedure that I did. You can fit the model based on the first 3 and then see if the residuals still show some significant correlation. And then there exists significant stress. You can run, for example, the Box-Leung-Pierce test. I think I'll talk about that later on in the course. So just a suitable model that, okay, what parameters I have to estimate? No, there are no parameters that you have to estimate. You just have to look at the ACF and PACF. And you see which of these models is compatible with the ACF and PACF that you observe for the data. That is, you ask if the DGP is MA3, would you see an ACF or PACF like this? And so on for the remaining 3 options. Because we have said that you have to pick among the 4. We are not asking you a blanket or an open question. Okay. Any further questions? Anything else that Ranga, Nitya, and Raghav, the team there, do you think we need to revisit any particular concept, or I think things are okay?
I think nothing from the forum, sir.
Okay, there's one more question. This question is on prediction for considering that there is predictability in time series. How many data points in the past are good enough to start off the modeling exercise? So the TA team, do you want to answer that question? You want to take
the question is to start, sir.
Yeah.
It depends, right, sir, on a lot of factors.
The simple answer is there is no universal answer. It's very hard to say that because it depends on the model structure. It depends on what is the complexity of the process and the estimation algorithm that you're using. So there is no universal answer. You'll have, okay, I mean, if you go by a very rough guideline, if you can look at the number of parameters in your model, and let's say you have P parameters in your model, obviously theory tells you that at least you need n observations to get started off. P observations to get started off. But remember, we are not solving an exact or a determined problem. Typically, we solve an overdetermined problem. Right? That's very important to recognize in time series analysis. When I am fitting a model, so let me explain that. So let's say I'm fitting a model, an AR1 model. So minus D1 Vk minus 1 plus Ek. Obviously, the unknowns, if I look at it from a strict viewpoint, the unknowns at each k, and at this k, so you have each k is minus D1 and Ek. Now, minus D1 is going to remain the same across all k. But at any single instant in time, I have two unknowns. Therefore, how many ever observations you have, you will never be able to solve this in a determined way. That means you'll always have number of unknowns greater than number of observations. But the good news is that we may not be interested in recovering Ek. The reason is Ek for the data that I have is from a specific realization. So even though I recover Ek, there is not much use. Whereas minus D1 is a common property of the ensemble, of the time series process, random process of generating Ek. So that I want to capture. But Ek, I'm not interested in estimating Ek. However, what is time series modeling? It's all about from the single, let us imagine a crop. A farmer grows a crop. From this, let's say it's a sugarcane farm or whatever it is, from the single plant of sugarcane that I have, its growth over a period of time, I should be able to comment on the entire crop. The crop is the ensemble. That's so that here corresponds to properties that are common to all realizations of V. Minus D1 is a parameter that's common to all realizations of Vk, whereas Ek is the one that is specific to the realization that I have. If I change the data for the generating process, if I observe the experiment data again, the D1 will remain the same, but Ek will be different. However, the statistical property of Ek will be the same across all data sets. So we are interested in minus D1 and let's say the variance of E, assume that Ek has zero mean. It's okay to assume that. So these are the two unknowns that I'm interested in, not these ones, not the ones that are above. This you can never solve because you will always have fewer observations in the number of unknowns, and I'm not interested. So now you know the answer. I have two unknowns to estimate. I need at least two observations. But the problem is, since each data point has a new unknown that is coming in, I will never be able to solve this in the time domain exactly, but in the autocovariance domain, that's what Euler-Walker equations are. That's why they are very popular. In the autocovariance domain, I can set up exact equations for D1 and sigma square E. I just need two equations. I cannot set up those two equations in a time domain because I always have more unknowns than the number of knowns, the number of data points. When I go to autocorrelation domain, I will be able to set up two equations, two unknowns, and solve it exactly, provided I know the theoretical ACFs, the theoretical moments. Now, therefore, the question boils down to how many data points do I need to get a decent estimate of the autocorrelations? That again is debatable. You will have to specify the error bounds and so on. So typically, you can start off, if it's an AR1 model, it's sufficient to start off with 30, 40 data points. And then you will have to recursively update it. So otherwise, there is no unique answer per se. To how many data points for starting off model estimation. So if you have 10 parameters, yeah, maybe you want to have at least 200 or 300 data points. And so there is sufficient degrees of freedom for you to reduce the variability in the parameter estimate. How powerful are the AR models? Chaitanya asked a question. And how often they're used in the industry? Oh, AR models are quite popular. I wouldn't use the word powerful. I would use the word popular because we're looking at celebrity status of AR. Of course, they're popular because they're very effective. But for many processes, AR models can fail to deliver the goods, because if the process is non-linear, for example, or if the process is high order MA, or it's a fairly high order ARMA, then you will need many, many parameters in AR to explain. In which case your AR models may not work. But for a variety of processes, yes, AR models are preferred because of the ease of estimation. And they lend themselves to easy analysis. So they are used in industry quite popularly. In fact, the system identification equivalent of AR model is ARX model, which is very popular in the industry. Okay, any other question? So do we assume that we are done? So do we, okay, one more question, got just under some guidelines. Okay. In case of highly volatile stock prices, in what way time series analysis will be useful? Of course, they are very useful. Time series analysis is useful for analyzing all such data. When you say highly volatile, I presume, sir, that you are actually talking about variability that keeps changing. There has been a lot of work done to model such data. And somewhere in the 80s came up this Arch and Garch models due to Engel. And by the way, Engel was a Nobel laureate, not just for contributing to these models, but other contributions to econometrics. But for a long time, modeling this highly volatile stock prices was a challenge. It doesn't mean that it's solved now. But yes, people found some good models to explain the high volatility. You will have to pick the right functional relationship, that is whether it's linear or non-linear, and also whether the driving force is a Gaussian white noise or some other white noise. So typically, you will want to assume linearity, but unfortunately, linear models are, let me tell you something. All the models that we are fitting are aimed at modeling the conditional expectation, because that's the best prediction, or we say the conditional average. So the AR model, MA model, ARMA model, all of them are actually modeling the conditional average, whereas volatility has got to do with the variance. So there are models such as ARCH, GARCH, and their variants, which cater to modeling the variance, the changing variance. And you may have captured the conditional expectation very well with the ARIMA model, and you may have made a good prediction. But the variance of the predictions, that means the bounds that you draw on your predictions, they depend on the volatility. And again, there are two classifications, whether this volatility is a function of the past or it is just changing from time to time instantly. So there is something called unconditional heteroscedasticity versus conditional heteroscedasticity. The unconditional ones you can manage with the box cost transformations. It's a conditional ones that are a lot more subtle, and that's where your Garch and Arch models like Garch and Arch like models can come to help, and that's what Engel actually contributed significantly to. Okay. So I suppose there are no further questions. And are there any unanswered questions in the doc, Nitya?
No, sir.
Okay.
No, sir. There are no questions in the talk.
Right. Okay. So then shall we call it off, and we can have another live session maybe in another 3 to 4 weeks again, maybe at the end of the 7th week, something like that. And then, so I think a couple of more live sessions will certainly help before we complete a course. We can have another live session either 7th or 8th week. We'll send out an announcement.
Right, sir.
Okay. But yeah, I'm glad some very interesting and probing questions, thoughtful, insightful questions, thought-provoking ones. Good. Very nice. And I hope a lot of them will actually take the exam, will register for the exam. And that's what will make the course complete. Okay. So I think we can close the live session for today, and we'll take the remaining questions on the forum. And of course, there is always the next live session to address the new questions that are there. Yeah, thank you. Thank you very much.
Thank you, sir. Thank you, Professor. Yeah, I will stop the live now.
Yes, Balaji, thank you very much. And the recording of this will be made available, yeah?
Yes, sir. The same link will be, we can see the recorded one, sir.
Okay, very nice.